Hello, in this video I'm going to speak about the foundation, and we want to start with the foundation construction. What about the excavation? How we specify the excavation, the extent of the excavation, and do we need or to pour plain concrete? Maybe. And if we use it, why? What are the advantages of having plain concrete? And what about the steel bars? How we can specify the number of steel bars. In this picture here, you can see that I have a footing after the excavation, and the contractor was lucky because the soil was cohesive, so he could have this excavation and in a simple way. And you can see here they already put some bars, some as datum for the construction purpose. And here you can see that they already poured some plain concrete in the foundation itself. So the plain concrete has the advantage of providing a level to put the steel bars above it. It can provide also additional cover for the steel from the underside of the foundation. Now, when we look at that, how we can specify this extent of the excavation, how big this footing can be, and how deep it should be. That we will go through that today with the requirement of the code and with the scientific and engineering rules. And here, after we have the excavation, we can start placing our steel bars. And as you can see here, this gentleman is placing the dowels here for the columns. And here we have two layers of reinforcement, because we have here the dowels for column and here for another column. So that's here is a combined footing which will carry more than one column on it. So if this area will exceed the limits, or if these two areas, for example, are very close to each other, we prefer in many cases to say, okay, let's combine them together and create a combined footing. And in the combined footing, you have two layers of reinforcement. Each layer has the reinforcement in two directions. And these pictures are from one of our projects in condominium building in Toronto. Now, the foundation design steps. We calculate the foundation area and we estimate the thickness based on our experience. And then you can check what your estimation is, that safe enough or not. What does it mean safe? Against what? Against bunching shear and against the one-way shear. What they are, we will talk about them later. And calculate after that the reinforcing bars. So after we do that, we know the area from the soil pressure. We know the thickness based on the experience, and we make sure that we are safe in the shear. Now we can calculate the reinforcing bars, and the crew can put the rebars on the site, as you can have these pictures. Now the design steps of the foundation. We wanted to know the foundation area. We have to estimate the thickness based on our experience, and then we want to make sure that the thickness is strong enough. What does it mean strong enough? It should be strong against bunching shear and one-way shear, and we will go through that later in this video. And after we calculate that, we want to make sure that the reinforcing bars are enough to resist the tensile force in the foundation. We will go through that in this video. So now let's look at the effect of the soil on the foundation. When we have a column like that sits on the foundation, normally we assume that it has the normal pressure is homogeneous underneath the foundation. However, if you have cohesive soil, you have less pressure underneath the column, and the pressure increases as you go outside to the edges. But if you have granular or gross soil, the maximum pressure will be underneath the column, and the pressure decreases as you go to the outside. In most of the time in the design cases, we assume that we have a uniform distributed load underneath the foundation. Now let's look at what are the requirements for the design and the steps. We want to calculate the area. How we can calculate the area? It's based on the allowable stress of the soil and the applied load. We have to calculate the applied load and know the allowable stress of the soil. Now we can say, okay, I need 4 square meters footing, then I can have foundation 2 by 2 or 2 by 3, well, whatever the area will be. The second thing is we have to estimate the depth, and for the depth I have to satisfy the one-way shear risk, and the other one is the two-way shear or the bunching shear. After that we have to calculate the reinforcing bar to resist or to take the tensile force which are created from the bending moment at the face of the column or the wall. We will go through these steps 1, 2, and 3 in each item soon. Now, if we look at the first one, how to calculate the area underneath the column. If I have a point load, the column here as a point load, and this column is centered over the foundation, now you have a uniform distributed pressure underneath that. This pressure is Q equal to P is this force divided by the area of the foundation. Now, when we design it, we know the Q allowable. Q allowable is we get that from the soil report. The soil report can tell us, for example, the allowable pressure for the soil is 200 kilonewton per meter square. So that means if I have 1000 kilonewton from the load and I know that the allowable pressure is 200, then I can say 1000 divided by 200, then I need an area of 5 meter square. Then I can have 2 by 3, for example, it will give me 6 meter square. 2.5 times 2.5, that will be even bigger. Okay, so I want to make sure that the area will give me at the end stresses on the soil less than the allowable stresses which I can get from the soil report. So PS is the unfactored load acting on the foundation, and QA is the allowable stress, and A is the area of the foundation. So I know PS from my calculation from my building, and QA is the allowable stress. I know that from the soil report. Now I can calculate or I can estimate or choose an area which will make these conditions valid. I have to make sure that QA, the allowable stress, times this area bigger than PS. When I choose the area, I have to look at the surrounding area on the site. For example, can I exceed the property line if I have my foundation in a column at the edge or not? Do I have neighbor or not? Now that are like when you design the foundation, you have to look at many parameters, especially in the neighborhood. So now we can say I can get the area of the foundation. However, we assumed that the load is centric on the foundation, but sometimes based on the conditions you can get the load in the center. For example, if you have your column here at this location P and you can't have centered because here is a property line and you can't go in this direction, so you still need to have along this length for the foundation. Now your column will not be at the center of the foundation, which will have some eccentricity, we call it E here. So the load is not centered on the soil on the in the center. Now you can see more stresses at this end less than this one. So the stress is not uniform as you see here, but it has more stress towards the load direction. Now this here can be calculated as you have a bending moment M and you have a point load P. So you can have now this M and P, and here that's the original distribution from P, and when you add the effect of the moment, then you can have the more stress at this side and less stress on this side. And how you can calculate the stress here is this stress on the soil P divided by A, that's normal stress, we know that, and here plus or minus M times Y divided by I. What are they? The M is the moment here, and this moment will be P times this distance, that's the bending moment. So I have moment here because I have eccentricity, so I can calculate my moment, and Y here, Y is the distance from the centroid axis to the point where the stress are being calculated. For example, that's here If you want to calculate the stress here, that will be this distance will be your y. If you want to calculate the stress in this at this location, that will be your y. And I is the moment of inertia, which is will be b times h to the power of 3 divided by 12. That's the stresses based on the bending moment and normal force. That's a combination of them. Now, here you have again, our case will be focused on the concentric load, so there is no eccentricity. We have eccentricity equal to 0. I have normal stresses. When I select the area, so I have the dead load of the building plus the live load. When I divide that by the allowable stresses, then I can get my area. And sometimes I can have some load combination. If the wind load is there or the seismic load will be considered, then I have to have another load combination here. Now, after we calculated already the area of the foundation, we want to check the depth or choose the depth of the foundation. When we choose the depth, we estimate a specific depth based on the experience, and then we have to check for one-way shear and two-way shear. Now we will focus first on the one-way shear. In the one-way shear, when you have the foundation in this case as a square foundation, and you have this column, normally you have the maximum shear from the structure analysis. The maximum shear is at the support where you have the reaction, but here that means you have the maximum shear will be at the face of the column, but because the forces which are close to the column will not create shear because the force will go direct to the column, so we calculate the shear force at a distance equal to d from the face of the column. So if I know this distance and I know already this width, and I know I multiply this area by the Q net factor, then I can calculate the force, the acting force at the foundation. So if you have a wall, in this case, that will be the one-way shear along this line. That will be your shear, critical shear section. If you calculate this stress here, how much the stress you have times this area, you can get the force which is acting at this face, and this force will be Q, the factored net soil pressure, times BW, this length, times this distance, and this distance here is L, is this length, minus T, assuming this T is the column width, divided by 2. Now I have this length and this length. So this length, when I divide it by 2, then I have this length, and I subtract the distance d, so I have this dimension. So if you calculate these dimensions and you multiply by this length, you can get the area. When you multiply that by the Q factor, the factor net soil pressure, then you can get the shear force, the acting shear force. Now I want to calculate the resistance force. So the resistance force VC of my cross section equals to beta times lambda times F prime C square root times phi C times the square root of F prime C times BW times D. I will say it one more time. VC equals to beta times lambda C times phi C times square root of F prime C times BW times D. So beta here, you have different ways to calculate them. You have three clauses and you have to take the smallest one. To make it simple, I choose the simple method, which gives me beta equal to 1.18. So 0.18 is beta, and lambda for the normal concrete, I have it 1. Phi C 0.65, F prime C, that's what I choose for my foundation. BW is this, here is this cross sec, is this length, and D is this depth of the foundation. So I get VC, and we have to make sure that VC is bigger than VF. If that's not the case, you have to increase your foundation depth. Otherwise, you will have a one-way shear problem. Now, if you have finished your one-way shear check, you want to check the two-way shear. In the two-way shear, when you have a column like that, and this column will, it depends on the cross-section area of the column and the depth of the foundation. So if you have a nail, so you can hammer the nail through a timber piece, and but if you have the head of the nail upside down, then you can't hammer it because of the resistance. With the same concept, we can check for the bunching shear of this column, and there are two-way, like two expressions: bunching shear or two-way shear. So the column can penetrate through this foundation. So to check that, uh, many experiments were carried out, and the experiments showed that along this parameter here, inside that will be the cone of the punching. So this blue area outside, if you calculate the blue area and multiply the blue area by the factored soil pressure, then you can have the shear force, the bunching shear force. So here from this equation Q, the factor net soil pressure times the area of this foundation, minus T again is CT here, so that's the width of the column, plus here you have a half of D and half of D. When you add them together, you have D. So you have here T or CT plus D, that will be this length. And because that's square, you can have it like T plus D square or CT plus D. Here we have the equation with T, and on the drawing you have it at CT. So the total force now here is QF times A minus T plus D square, and that you can get the bunching shear force. Now, what is the resistance? So the resistance of the concrete for bunching of the cross section is capital VC. That's the resisting force. We want to make sure that capital VC is bigger than VF. If that's the case, our foundation thickness will be safe against the bunching. So VC is the biggest, the shear force, as the small VC times BO is the perimeter of this cone here, times D is the depth of the foundation. So D is the depth of the foundation, and BO is 2 times C plus C1 plus D, this one here, and plus 2 times CD plus D. So if you calculate this length and calculate this length, so you calculate the whole perimeter here, that will PO. So if I calculate my PO times the depth and I multiply that by VC, then I can get the capital resistance VC capital, which can be compared with the VF. Now, here let's go to more details about how we can calculate VC. So VC is the smallest value of these three equations. So you can have it here. If you have a rectangular column, you have to get the longest column size divided by the shortest column size. You can have beta C. So beta C is 2 divided by beta C, and you can calculate this amount, and you compare this amount with this here, and this equation depends on alpha S. Alpha S is the location, consider the location of the column. So for interior column, you have alpha S equal to 4. For edge column, it's 3, and for corner column, it's 2. And BO, D is the depth, and PO we calculated from here, and you calculate this amount. And you can calculate without considering any of this parameter. You can use this equation, which is 0.38 times lambda C times phi C times the square root of F prime C. So you have to calculate the 3 and take the smallest value of that. To make it simple, I choose already this amount to be used in this example. So this here, you can use it as VC, small VC. So it will be 0.38 lambda equals to 1, phi C 0.65 square root of F prime C. The concrete which you choose, you can calculate this amount. You can calculate PO, and you can your depth, what you choose already. And then you have to calculate VC, the resisting shear force of your foundation, and compare it with the acting force VF after subtracting the cone area from it. If your VC is bigger than VF, then your thickness of the foundation is safe enough, and then you can go to the second step. And the second step will be determining the amount of reinforcement. So when you have your foundation in this case with this cross section, now to calculate the bending moment, this footing will bend from the soil pressure, and you have here the column. It will bend along this side, so you can have it as if it is a cantilever, as a balcony, and that's your interior, that's your support. So it's exactly as a cantilever or balcony, but upside down balcony. So now what is the force, or how I can calculate the bending moment? When I know my factored net soil pressure, QFN factored, and I multiply that by B, this length, and I multiply that by this F. And this F is the distance to the face of the column, is not with the distance to the face of the column. Now when I calculate this here, I get the force which is acting in this area, and this force will be acting in the middle of this distance. So the force will be acting with a distance of F divided by 2. Now I have MF equal to QFN times B times F times F half. Okay, so we can calculate this bending moment. And here, if you have this column or wall concrete, then you can, the cross section will be at the face of this column. If you have a circular column, then you have to have imaginary square column, and then you calculate the bending moment around that. If you are using masonry wall, you have to go halfway between the middle of the wall and the edge of the wall. And if you have a footing and that support structural steel with a base plate, then you can have halfway between the face of the column and the edge of the face plate. So what I'm trying to get here is, it depends on the type of the column and the type of the material also of this column or wall. It can have some variation for this distance where you have to calculate your bending moment around. Now when I calculate my bending moment, and I can divide it by my depth, and my depth is safe now against one-way shear and two-way shear, the moment divided by distance, that gives me a tensile force, right? When I divide the tensile force by 0.85, the material factor of safety for the steel, times Fy, then for the steel, for example, Fy for our structural steel, or our steel bars, is 400 Newton per millimeter square, then I can get my area steel. Now when I get the amount of area steel and divide it and say, okay, I will use a number 15 or number 20 millimeter diameter, and for example I can get 20 bars. This 20 bars, what you calculated, will be distributed along this side. So for example, if you have here 3 meters 3 meters and you have 21 bars, I'm changing the number now, 21 bars, and the 3 meters, that means every meter will have 7 bars. Okay, so you can have for every meter 7 bars. So the amount of steel what you choose, it will be distributed perpendicular here, because that will be the to that will be the face which you calculated the moment around. You need the area to be in this direction. After you finish that, you have to take the bending moment along the other side and calculate the area steel and put your reinforcing bars along this side. So the foundation has always two direction of reinforcement, and if you have a square foundation like that, your reinforcing bars in this direction will be equal to this direction. Now when you choose your reinforcing bars, you have to look at the area steel minimum. The code requires that 0.2% of your cross section area of the foundation to be covered, and the maximum spacing between the bars, maximum spacing between the bars will be the lesser of the thickness, or 500T. And here you have also the maximum bar stresses. When you have your bars distributed inside along your foundation, you want to make sure that your bars have enough, your bars have enough anchorage length, and sometimes you need to get the bars sticking up with an L shape like that to provide anchorage. So the reinforcing bars itself has more details, and that can be a topic for itself. And here, when you look at what we have done to carry out a foundation design, we need to determine the area of the foundation which we have done already, and we have to also to get the depth, to estimate the depth of the foundation. And after we estimate the depth, then we can have the one-way check, the one-way shear and the two-way shear. When we estimate the total thickness, we have to subtract 75 millimeter for concrete cover and maybe another 10 millimeter for the radius of the bar. So if you say I have 500 millimeter thick concrete, that means your depth is 500 minus 75 millimeter cover minus 10 millimeter for the steel bars. So 500 minus 85, that will be 415 millimeter. That will be your D, what you have to choose in your equation, what I just went through. That's for the one-way shear and the two-way shear. When you are sure that your depth satisfying the shear requirement, the foundation depth is strong enough, then you can calculate the reinforcement, and this reinforcement will resist the bending moment to be accurate at two sides of the columns, and you will have the reinforcing in two perpendicular direction. Thank you.